The key innovation of our approach is the use of a 3D Gaussian representation of the object. This representation allows us to acquire explicit 3D shapes and enables the simulated continuum to generate object mask during the simulation process. These object masks serve as 2D shape surrogates, facilitating geometry-aware guidance during the estimation of physical properties. Hello everyone. Today I would like to share our recent work, Gaussian-Informed Continuum for Physical Property Identification and Simulation, which was accepted by NeurIPS as an oral paper. Basically, this work proposes a pipeline to both recover the geometry and infer the physical properties of the objects from multi-view video sequences. Here is the background of this work. When we see a video of an object interacting with the environment, such as dropping it onto a table, we can usually deduce the object's properties with just a glance. For example, we can easily tell whether the object is soft or hard based on how it develops. A hamburger might appear softer, while a potato might seem harder. However, estimating the properties with only visual observations remains challenging for computational perceptual algorithms. Therefore, in this work, we propose a comprehensive pipeline to recover both the geometry and physical properties of objects from visual observations alone. The key innovation of our approach is the use of a 3D Gaussian representation of the object. This representation allows us to acquire explicit 3D shapes and enables the simulated continuum to generate object mask during the simulation process. These object masks serve as 2D shape surrogates, facilitating geometry-aware guidance during the estimation of physical properties. So this work mainly consists of two parts. The first part focuses on reconstruction. Specifically, we propose a new dynamic 3D Gaussian framework based on motion factorization to recover the object as 3D Gaussian point sets across different time states. Furthermore, we develop a cost-to-fun filling strategy to generate the density fields of the object from the Gaussian reconstruction. This allows for the extraction of object continuums, along with their surfaces and the integration of Gaussian attributes into these continuums. The second part involves physical property estimation based on the differential simulator and the target trajectory extracted from the first part. Using analysis by synthesis, we iteratively update the physical parameters to ensure that the simulation behaves consistently with the target trajectory. With the recovered geometry and estimated properties, we can apply these results to various applications, such as simulatable assets and deformable object manipulations. I will discuss these applications in more detail later. After going through the whole pipeline, we can identify three key questions that remain unsolved. The first question is how to reconstruct the trajectory of the object from multi-view observation. To enable object simulation, the next question is how to transfer the reconstructed geometry to simulatable continuum based on the reconstruction. Using the reconstructed continuum, we can perform a simulation to generate the simulated trajectory. The third question is how to represent the object's trajectories in a way that allows for straightforward comparison during parameter estimation. With these components all set, we can perform analysis by synthesis to iteratively update the physical parameters. Given a current estimate of the parameters, we can simulate a trajectory and compare it with the reconstructed one. The error between these two trajectories will be backpropagated to update the parameters accordingly. To tackle these issues, we return to the first part regarding object dynamic reconstruction based on Gaussian splitting. The dynamic 3D Gaussian pipeline follows existing frameworks that simultaneously maintain a canonical 3D Gaussian point cloud and a deformation field modeled by a neural network to warp the canonical shape into object states at specific times. Specifically, The canonical shape is a linear point cloud with Gaussian attributes assigned to each point, which forms a Gaussian point cloud. The neural network outputs both the offset of each basis at time t and the coefficients of each point at time t. The final offset of that point at time t is determined by the linear combination of the output basis with the output coefficients. Rather than directly regressing the offsets with FMP, we employ Fourier-based modeling, which decouples the motion into basis and coefficients, which provides more flexibility to model the trajectory. For example, since they are only related to time, we can reuse the output of motion basis. This design can greatly increase the efficiency. Finally, given the estimated Gaussian point cloud at time t, we can perform Gaussian splitting on the point cloud at various viewpoints and compare the rendered images with captured ground truth. We can simultaneously update the canonical shape and the parameters of the network. Up to now, we have reconstructed the object trajectory using a 3D Gaussian point cloud representation. However, the reconstructed Gaussian particles are primarily used for rendering, meaning that most particles are located near the surface. In other words, they are not evenly distributed within the objects and cannot be directly used as a continuum for simulation. Therefore, previous work has employed internal feeding based on reshooting. Essentially, they sample rays from various directions and check if the rays intersect the high opacity boundary of the object. However, this method is time-consuming and not robust, as different parts of the boundary may have varying opacity values, making it difficult to determine an exact threshold. So the question now becomes, how can we generate simulatable continuum from 3D Gaussian point clouds? One important consideration is that since the point clouds are Gaussian-informed, we can perform Gaussian splitting to render depth maps of the object from various viewpoints. A straightforward approach to generating a continuum is to first sample particles throughout the entire workspace and then project these sampled points onto the depth maps to fill out points that lie outside the object. Intuitively, this method should work. However, because the depth maps are rendered using alpha blending, they often penetrate the object, leading to uneven surfaces. Therefore, we propose a cost-to-fun feeding strategy to iteratively generate density fields of the object based on the reconstructed Gaussian point clouds and the internal particles filtered by the rendered depth maps. The resulting density fields will be used to both extract object continuum and inject Gaussian attributes into particles. Basically, given a cost density volume, we use the particles to retrieve the voxels and assign values to those voxels. Next, we sequentially perform upsampling, mean filtering, and reassigning the field at each iteration. The first two operations produce more fine-grained shapes, and the reassigning operation ensures high densities at the surface to avoid over-erosion caused by the first two steps. Therefore, with only 4 or 5 iterations, we can generate a density field that will represent the object shape. Here are the visualizations of point clouds generated by this method. You can see that our method can generate more precise shapes. So far, we can generate a continuous field from the density values ranging from 0 to 1, allowing us to easily sample this continuum by setting a threshold. This effectively addresses the first issue I mentioned earlier. Thanks to the density field representation, we can easily address the remaining challenges, such as setting appropriate thresholds to sample point clouds as object surfaces. Additionally, we can assign Gaussian attributes to the point cloud to facilitate Gaussian splitting. Specifically, the grid size is treated as a scale of the Gaussian kernel, while the density value is used as the opacity attribute. With these assignments, we can render 2D object mask during simulation. With these components all set, we can perform analysis by synthesis to iteratively update the physical parameters. Given a current estimate of the parameters, We perform simulation and generate a simulated trajectory. We next use the aforementioned methods to retrieve the object surface and use Gaussian splitting to render 2D mask from various viewpoints. Finally, by comparing the simulated and targeted trajectory, we can compute the current error between these two trajectories and backpropagate the error to update the parameter accordingly. So this is basically how this pipeline works. Here are some experimental results. We first perform the system identification on various types of object instances, including Newton flows, non-Newton flows, elastic objects, plasticine objects, and granular objects. As you can see, the proposed method achieves better system identification performance on almost all parameters compared with the baseline. Below is a visualization of the simulation using the reconstructed geometry and estimated parameters. Here is a video showing the simulation results based on our reconstruction and parameter estimation. As you can see, we can reconstruct the trajectory similar to the ground truth. We can also switch the parameters to different objects, which can simulate different effects. Here is another video demonstrating our simulation on a different dataset, comparing the trajectory with both the baseline and the ground truth. As you can see, our method simulates the trajectory more consistently with the ground truth, indicating that it can estimate more accurate physical properties that better reflect the object's behavior. Here is a visualization of considering the reconstruction results as simulatable assets. We can simulate various effects of the reconstructed objects by changing either the properties or conditions. To demonstrate the potential application of our method in real world, we further employ our method to the real captured data. Here are the digital twin demos. We perform shape reconstruction and system identification on real-world objects and perform the same manipulation on both simulated and real-world objects. The results show that the behavior of the simulated objects augmented with our estimated properties are consistent with the behavior of the real-world objects. That's all. Thanks for your watching.